A clay tablet. It holds a secret, one that rewrites human history. For centuries we gave the Greeks credit. They invented advanced mathematics. But this Babylonian artifact tells a different story. You'll see the timeline of scientific thought transformed. This is a 4,000-year-old list of numbers. It contains a form of trigonometry, a form no one believed possible for another 1,000 years. And it reveals something about the anonymous genius who made it. What does true innovation look like? When it comes from a place and time we barely remember. That list of numbers had a long journey before it ended up in a museum. It began in the dry ground of southern Iraq, a place once called Babylonia. This was the early 1900s. That region was a source of fascination and also a lot of looting. Ancient sites were being torn apart by people looking for treasures to sell. Artifacts came out of the earth and went into the markets of Baghdad, changing hands, their origins getting lost. It was in that chaos that this tablet came to the surface. And this is where Edgar J. Banks comes in. He was an American archaeologist, a diplomat, an adventurer. Some think he was the model for Indiana Jones later on. He worked as a consul there and had an eye for antiquities, both for study and for selling to collectors back in the US around 1922. He bought this specific clay tablet. We don't know exactly which site it came from or who last held it in ancient times. It was just another piece in that stream of history leaving the desert. The object is modest. It fits in your hand about the size of a smartphone but thicker, like a small stone. Its surface is covered in precise, wedge-shaped cuneiform marks pressed into the soft clay over 4,000 years ago. One corner is a little damaged, a small scar from its time underground. Banks sold the tablet with many others to a wealthy New York collector named George Arthur. Was a publisher fascinated by the history of education, and he built a remarkable collection of math and science texts. In 1936, he left his entire collection to Columbia University. And there, as 322, the tablet sat on a shelf. It was known as an ancient math document, but its deeper secret stayed hidden. For decades, it was just a curious relic, a time capsule no one had opened yet. Scholars looked at its columns of numbers and saw a trigonometric table, but they saw it through a Greek lens. They assumed it was just a crude forerunner to the work of Hipparchus. They were looking at a masterpiece and seeing a rough sketch. The true nature of its code and the revolutionary mind behind it just waited quietly in the library for someone to finally ask a different kind of question. There was this tablet. 322. Otto worked on it. He was a historian of mathematics. He came to America in the 30s, and in the 40s he looked at this tablet. He cleaned up the numbers, corrected some readings, published the first real analysis. What he saw was a structure. 4 columns, 15 rows. It looks like a ledger at first, but the numbers were too intentional for that. The first column had a sequence like decreasing fractions. The second and third columns, pairs of whole numbers, and when you looked at them together, a relationship. For each row, you take the number in the second column, square it, and the number in the third column, square that. The difference between those squares is itself a perfect square. That's the pattern of a Pythagorean triple. 3 whole numbers for the sides of a right triangle, like 3, 4, 5. The tablet was a table of these triples, and it was accurate. That was the first shock. The Babylonians, 1,000 years before Pythagoras, they knew about these triangles. They had a list, 15 triples, some with huge numbers like 12,709, 13,500. To generate these without calculators, that's a serious feat. So the mystery deepened. It wasn't just that they knew the idea. Someone had gone to great lengths to make this specific, ordered table. It was a tool. But for what? Measuring fields, building? The purpose was still locked away, and the real genius of its design was misunderstood. Everyone too, they saw it through Greek geometry. A list of triangle sides. They were admiring the flowers but missing the garden. The tablet's true nature was something else. A different kind of mathematics hiding in plain sight. The numbers had a pattern. That was the first clue. But the full picture came into focus slowly. Scholars had these columns, these neat rows, perfect squares. They saw it was about right triangles, but the real breakthrough was seeing what this list actually was. It wasn't just a random set of measurements. It was a deliberate table, what we now call Pythagorean triples. Take the simplest triangle, 3, 4, and 5. 3 squared is 9, 4 squared is 16. Add them, you get 25, which is 5 squared. That equation, a squared plus b squared equals c squared, that's the Pythagorean theorem. And 3, 4, 5 are a triple, 3 whole numbers that make it true. The Babylonians didn't just know one triple. This tablet lists 15, and they aren't simple, they're enormous, precise. They follow a hidden order. Look at one row. The second column gives 12,709. The third column gives 13,500. You square both, you find the difference, and you get another perfect square. Its side is 18,541. So the triple is 12,709, 13,500, 18,541. That's a massive set of numbers, not obvious at all. To find that without our tools, to even know such a thing existed, that required a deep grasp of number theory. That was the staggering fact, the one that rewrote history. Here was a systematic, advanced understanding of mathematics, etched in clay, from a place called Babylonia. Around 1800 BC, Pythagoras, the man with his name on the theorem, wouldn't be born for over 1,000 years. This tablet wasn't a crude guess, it was the work of a master. Using a method we are only now starting to fully appreciate, the Babylonians built their math on 60, not 10 like we do. They used a base 60 system, we still see it today. 60 seconds in a minute, 60 minutes in an hour. A circle has 360 degrees, that's 6 times 60. These aren't accidents, they come from Babylonian math. Their notation was simple, 2 symbols pressed into clay, a vertical wedge for 1, a corner mark like an arrowhead for 10, to write 3 wedges, for 37 3 corner marks and then 7 wedges. It was additive, easy to read. But their leap was place value. The value of a symbol changed based on its position. Like our number 123 where the 2 means 20. They did that with powers of 60. A wedge in the first position meant 1. That same wedge, 1 position to the left, meant 60. The next position over 3,600, 60 times 60. This was a revolution. The Romans later had numerals where x always meant 10. Babylonian math was fluid. It let them handle huge numbers, and it let them work with fractions. A wedge in the place after the 1's column could mean 1/60th. So that tablet with the large, precise triples, it's not magic, it's the output of a sophisticated machine. Their base 60 system was the engine. It provided a framework for abstraction, for seeing numerical relationships a rigid system might miss. This wasn't primitive arithmetic, it was a powerful foundation. It let someone 4,000 years ago think in ways we're still decoding. The real question is what they were thinking with it. What was the purpose of this table? For a long time people saw it as a practical tool, a trigonometric table for the ancient world. The logic was clear. These Pythagorean triples, they give you ratios. If you're a Babylonian surveyor, a mash, measuring a field after the floods, you need right angles. Or if you're an architect laying out a foundation, you need precision. This tablet could give you that. You could use a Rho's ratio to find a slope, to calculate a length you couldn't measure directly. It was a brilliant idea, it fit the evidence. It made the tablet useful, a piece of ancient engineering. And it placed Babylonian math as a precursor, a stepping stone to Greek trigonometry. A necessary but simpler beginning. That interpretation held for most of a century. It was satisfying. It solved the mystery, or so we thought. Then in 2017, a mathematician named Daniel Mansfield looked at it again. He and his colleague weren't satisfied with the stepping stone idea. They asked a different question. Not what could this be used for, but what mathematical principle was it built on? They dug into the exact selection and order of the numbers, and they found something. The precision wasn't just good, it was perfect. The tablet's ratios are exact, using whole numbers with an accuracy that our modern sign-based trigonometry with its messy decimals can't match for these specific calculations. This wasn't a crude tool. It was a masterpiece of a different design. Mansfield proposed an idea. 322 is a trigonometric table, but of a kind we abandoned. We think of trigonometry as the study of angles and circles, sines, cosines, tangents. The Babylonian system, he argues, was built purely on ratios of sides. It was a trigonometry of exact proportions, not approximate angles. Instead of starting with an angle and finding a sine, their system started with a desired slope or ratio, and the tablet gave the perfect whole number triangle that produced it. This is a shift. It means the scribe wasn't just making a list. They were constructing a complete mathematical framework. one that was, for its purpose, more accurate and more elegant than the system that replaced it. The mystery changes. It goes from what it was to why we ever stopped using such an idea. What happened to this path? The person who made this tablet lived in the age of Hammurabi. That's around 1800 BCE, the old Babylonian period. It was a world of brick and canals, a bureaucratic empire. Cities like Babylon and Ur were huge, tens of thousands of people living in a tight grid. Canals everywhere for irrigation and for trade, and at the center the ziggurat, a man-made mountain. That scale of civilization required precision. It demanded administrators who could measure, who could calculate and record everything. The writer of 322 was almost certainly a scribe. Scribes were the elite technocrats. They were trained in formal schools, the tablet houses. Imagine a room where boys from certain families sat for years, mastering cuneiform, learning word lists, copying legal texts, studying mathematics. Their training was intensely practical. They needed to calculate the area of a field after the annual flood, after the Tigris and Euphrates reshaped the land. They had to figure out the exact number of bricks for a city wall, or the correct amount of grain for interest on a loan. Their math was the engine of the state, of commerce, of survival. So when you look at this tablet of Pythagorean triples, the first thought is it must be a practical tool, a reference for surveyors, for laying out perfect right angles for temples or land plots, and that's likely part of it. But then you look at the numbers, their size, their perfect order. The largest triple uses numbers in the tens of thousands. You don't need a triangle with a side of 18,541 units to measure a field, to build a canal. That scale is abstract, it points to something else. This is the crack in the wall between pure utility and pure thought. The scribe was solving a practical problem, how to generate useful ratios, but in doing that they stepped into a realm of pattern for its own sake, exploring the relationships between numbers, following a system to see where it led. This is the quiet birth of theory. The moment an administrator, surrounded by the day's needs, pauses and thinks, what if I try this? The tablet isn't just a tool, it's a demonstration, a proof of concept for a method. These individuals weren't merely clerks. Within the rigid structure of their society, they became the first theoretical mathematicians. They looked at numbers and saw not just quantities but relationships, waiting to be found. Those numbers were huge and they weren't random. They didn't just find them by accident. Nobody was sitting there trying out millions of combinations. They were making them. There was a recipe, a reliable one. Today we'd call it an algorithm. The Babylonians had a method, a set of steps that, if you followed them, always gave you a perfect Pythagorean triple. And the method is simple. It starts with two numbers. Call them P and Q. They had to be regular numbers in their base 60 system, which just means they make nice, clean fractions. And P had to be bigger than Q. From those two seeds, the whole triple comes out. You take P squared, subtract Q squared. That's one side of the triangle. Call that side, and then you take 2 times P times Q, that's the second side. B then P squared plus Q squared gives you the longest side, the hypotenuse C. You can test it with small numbers. Let P be 2, Q be 1, P squared is 4, Q squared is 1, 4 minus 1 is 3. That side of 2 times P times Q is 2 times 2 times 1, which is 4. That's side B, and P squared plus Q squared is 4 plus 1, 5. That's side C, and there it is, the oldest triple, 3, 4, 5. Now think about the scribe picking a different pair. Say P is 12, Q is 5. The math gets bigger but the rule's the same. 12 squared is 144, 5 squared is 25. 144 minus 25 is 119. That's a 2 times 12 times 5 is 120. That, 144 plus 25 is 169. The square root of that is 13. So the triple is 119, 120, 169. A much less obvious set, but it still works. That's the machinery behind the tablet. Every row on it comes from a carefully chosen pair of P and Q. The scribe wasn't just writing down triangles they found out in the world. They were exploring what a mathematical principle could produce. They were generating knowledge. And that's where it changes, from something practical to something deeper. Using this formula isn't just arithmetic, it's algebra. It shows they understood that numbers have abstract relationships you can work with, like objects. The scribe saw that the sides of a right triangle follow a quadratic pattern, a kind of dance between squares and products. They'd moved past just measuring shapes. They were operating on the rules that make the shapes. So 322 isn't just a table. It's a demonstration of computational power. It's like the output log of an ancient thought process, a formal procedure followed exactly. The person behind it wasn't just using math. They were programming, writing the code for a whole universe of right triangles and then printing out a clean, ordered sample of the results. The real artifact isn't the list of numbers. It's the invisible algorithm that made them. But who was it for? To know that, you have to see numbers the way they did. For them, math wasn't just a school subject, it was the language of everything. The river's flood timed by the stars, a field's shape changed by the water, planets moving overhead. Math was the script for order in a world that felt chaotic. And we know this because 322 wasn't alone. There are thousands of other tablets. Some are simple. A student's multiplication table practiced again and again. 2 times 30 is 60. 3 times 20 is 60. Those were the basics. Others are reciprocal tables. In a base 60 system, knowing the reciprocal of 2 is 30 or 3 is 20 that made division possible. It turned a hard problem into multiplication. Then you have the problem texts. They're like ancient word problems, digging a canal. So many workers, so many days, how deep? A triangular field, this side and that side, find the area. Building a wall with bricks of a certain size, calculate the number. These weren't abstract. They were training for the jobs that kept society running. The scribe was an engineer, an accountant, a surveyor. So in that light, a table of Pythagorean triples starts to fit. It belongs in that set of reference tools. Think of it as a master table, a piece of professional equipment. A senior surveyor or a temple architect or a teacher might have used it. They wouldn't derive the triples every time. They'd take this tablet from the shelf. Need an exact slope for a ramp on a ziggurat? Find the ratio in the first column, and the tablet gives you the whole number triangle to build it. Its creation points to a culture that prized precision. Record-keeping was sacred. A contract, a measurement, a star observation. Once pressed into clay, it was permanent, it was truth. And math was the highest form of that record. It described the world with an accuracy words couldn't match. So 322 sits at the peak of this. It's a sign of intellectual mastery, sure, but also a practical need for order, both cosmic and civic. The heavens moved in mathematical harmony. The canals, the granaries, the city's foundations should too. This tablet was a bridge between those ideas, the perfect ratios of the sky, used for the mud and brick of the earth. It wasn't made in a vacuum of pure thought. It was forged in the daily reality of a civilization that believed numbers could and had to rule everything. The tablet itself isn't perfect. You can see the damage along the edge. A whole section on the left side is gone, broken off, and even in the 15 rows that are left, there are small mistakes. In the 4th row, the second column shows the number 125. But the pattern of the whole table, the math behind it, means it should have been 115. It's just a copying error, a slip. Another row has a number that's a little off from the perfect sequence. These aren't major failures. They're just small stumbles, and that might be the most human thing about it. This tablet, for all its advanced work, wasn't some sacred, unchanging text. It was a working document, a reference, maybe a first draft or a master copy for other scribes. The scribe wasn't a perfect god of numbers. They were a person, sitting in a room doing long, complicated calculations by hand on wet clay. They got tired. Maybe they were interrupted. A number was wrong from a rough draft. The errors were baked into the clay and never fixed because for what it was used for, the table still worked. These flaws make the history feel real. We're not looking at a myth. We're looking at the fingerprint of a mind from 4,000 years ago. Then there's the broken piece. What was on it? The tablet we have only shows the results, the triples. But to use it, you'd need the starting inputs. Researchers like Daniel Mansfield have a theory. The original complete tablet almost certainly had more columns on the left. One column would have listed the key ratio, the relationship between the sides that defined each triangle's shape. Another column might have listed the generating numbers, the P and Q values that started the whole process. Some even think it could have shown the corresponding angle, though the Babylonians thought in ratios, not degrees. That missing part would have been the instruction manual. It would turn the tablet from a cryptic list into a real tool. You'd find your ratio in the first column, follow the row across, and there were your perfect whole number lengths for building or surveying. The absence makes you imagine. To see the complete object as it sat on a shelf, a full reference text. The broken state we have is a puzzle with a missing piece, so the whole picture is just out of reach. But the imperfections, the chip, the errors, they complete a different picture. They show us the individual behind the work, not a legend, a skilled professional doing a job, leaving behind a few small marks of their humanity in the eternal language of mathematics, that broken corner, those small errors. They place the work in a real time, a real place. But what this scribe did, its impact, it goes far beyond their own city. For a very long time, the story of mathematics had a clear beginning. It started with the Greeks, the 6th century before the Common Era. A man named Pythagoras. He founded a school, a brotherhood, all devoted to numbers. They saw mathematics as philosophy, as the key to understanding the universe. And they gave us the theorem that carries his name. Then later, centuries later, in the 2nd century before the Common Era, another Greek, Hipparchus. He's credited with creating trigonometry, the systematic study of triangles to map the stars. That was the narrative, the brilliant flash of Greek reason. Lighting the way out of ancient mystery. 322 breaks that timeline. It's not from the 6th century. It's from around 1800 before the Common Era, so it predates Pythagoras by over 1,000 years. It predates Hipparchus by more than 1,200, and this isn't about finding some crude precursor. The tablet shows a fully formed, sophisticated use of the very principles the Greeks would later explore. So what does that mean for the history books? It forces a shift, a profound shift in perspective. This isn't about taking credit away from the Greeks. Their contributions were immense. They gave mathematics a philosophical framework, a language of proof and theory that shaped all of Western thought. What the Babylonians had was a powerful, practical system for computation. They saw the how. The Greeks asked the why. They built a temple of ideas where the Babylonians had built a workshop of tools. The real story isn't one of replacement, it's about connection. Knowledge is a river, not a series of isolated springs. Ideas travel, they get traded, along with spices and textiles. The bustling crossroads of the ancient Mediterranean, the Near East, they were channels for this. It's entirely possible. Even likely that Greek scholars traveling, studying in places like Babylon, they encountered these older traditions. They didn't copy them, they absorbed them, they refined them. And they placed them within their own unique worldview. So the Pythagorean theorem, then, may not be a sudden discovery. It could be a brilliant codification of a principle known to scribes for a millennium. This changes the Greek miracle from a solitary event into a chapter in a much longer, more multicultural conversation. It rewrites the origin story from one of isolated genius to one of shared human inquiry. The anonymous Babylonian scribe and the famous Greek philosopher become part of the same effort, a sprawling effort to decode the universe with numbers. The tablet doesn't diminish the past, it deepens it, revealing a lineage of thought far more ancient and far more interconnected than we ever imagined. This precise list of triangles, what was it for? The answer isn't simple. It points to a culture where science wasn't separated. The leading theory for a long time was surveying. Every spring the Tigris and Euphrates would flood. It was life-giving, depositing rich silt, but it was also chaotic. It would wipe away the boundary markers between fields. When the waters receded, the king's surveyors, the MASH, had to restore order. They had to redraw property lines fairly, to prevent disputes, to ensure taxes were calculated correctly. That required geometry. To lay out a perfect right angle for a square plot, you could use a simple 3, 4, 5 triangle with a knotted rope. But what if the plot wasn't a simple shape, or the terrain was uneven? You might need a different slope, a different ratio. 322 provides a catalog of those exact ratios. You could find the precise whole number triangle that gave you the angle you needed for an irregular boundary. It turns abstract math into a tool for social harmony, for rebuilding a community fairly after nature's disruption. Then there is the astronomy theory. The Babylonians were legendary stargazers. They mapped the paths of planets. They predicted eclipses. They created the zodiac. Their entire calendar and religious life were tied to the sky. Their base 60 system is perfect for circles, which is why we still divide circles into 360 degrees. This tablet, with its focus on exact ratios, could have been a tool for celestial calculation. Imagine tracking the movement of a planet. Its path against the fixed stars isn't a straight line. To predict its position, you might break its journey into a series of right triangles in the conceptual sky. The long side represents the distance traveled. The other sides represent positional changes. The tablet's large, precise triples could provide the clean, whole number relationships. to make those calculations elegant and accurate, without the messy fractions that could accumulate errors over long observations. The same math that measured a field could, in their view, measure the heavens, because it was all part of one orderly system. A third, quieter possibility is education. We know from thousands of other tablets that scribal schools were rigorous. Students' multiplication tables. They solved word problems. They learned advanced procedures. 322 could have been a master reference for a teacher, a source of perfect problems for top students, or it could have been the crowning work of an advanced student themselves, a demonstration of their mastery over the algorithm for generating triples. The small copying errors we see might support this. The kind of minor slip a student might make under pressure. It would be a textbook example, not for building, but for thinking, training the next generation of bureaucratic minds to see patterns and wield systematic logic. The most compelling answer is likely a combination. This wasn't a single-use tool. In a society where the same elite scribes calculated brick counts, charted Venus, and taught apprentices, knowledge was fluid. A trigonometric table was a multi-purpose instrument. It calibrated the tools of the surveyor, the models of the astronomer, and the curriculum of the teacher. This single clay tablet becomes a keyhole. Through it, we don't see just one application. We see the interconnected mind of an ancient scientific culture, a culture that saw no barrier between the math of the earth and the math of the cosmos, because both were expressions of the same divine numerical order. The purpose of the tablet was, in a way, to serve that order itself. The marks in the clay, they're a precise language. Cuneiform, that word comes from Latin, it means wedge-shaped. And it wasn't written with ink. It was a reed stylus pressed into a soft tablet. Each press left a mark. A vertical wedge for the number 1, a corner-shaped mark for 10. To write a math text, the scribe had to plan the layout. Columns and rows aligned in the damp clay before it dried hard. This wasn't scribbling. It was a deliberate physical act. And the words they used for math, they were specific. In other Babylonian tablets, you see the terms us for length, sag for width, for the diagonal. These weren't vague ideas. They were the standard vocabulary of a technical field. The word for reciprocal that was fundamental. Finding the of a number, what you multiply it by to get one, that was a core skill. It was the key to division in their base 60 world. 322 itself, it's mostly numbers. But its silence is telling. It doesn't explain itself. It doesn't need to. Its format, 4 neat columns, 15 ordered rows, that speaks a fluent dialect. It's the same tabular format used for temple inventories, for ration lists. For tax records, the bureaucracy of empire ran on these grids of numbers. By using this formal administrative layout for a trigonometric table, the scribe was placing advanced mathematics inside official, standardized knowledge. This tablet wasn't a private notebook. It was a published document, meant to be read and understood and used by other trained eyes. The lack of explanatory text, that's not a sign of obscurity, it's a sign of confidence. It assumes the reader knows the conventions, knows the algorithm, knows the language. This shared tradition connects the anonymous author to a community of scholars, spread across time and cities. They were speaking the same technical language, solving problems with the same tools, building on a common foundation that turned individual insight into a sustained, collaborative science. The clay tablet was their network. The order of the triples is deliberate. It's a sequence, not a random list. The first column on the tablet, the one with the neat fractions, that's the key. It gives the ratio of the short side squared to the diagonal squared. In modern terms, it's about the slope, the shape of the triangle, and those numbers, they descend, from the first row down to the 15th. It's a controlled gradient, like a musical scale. Each note is a specific triangle shape. The sequence starts with a note that's almost an octave, and it steps down, note by note, to a much higher pitch. In triangle terms, it begins with a shape very close to a half square, an isosceles right triangle where the two shorter sides are almost equal. Then row by row, the shape changes. The triangles become more elongated. One angle gets sharper, more acute, the other gets wider. By the last row, you have a very sharp, skinny triangle. This isn't an accident, it's a design. The scribe was mapping a spectrum, creating a complete set of reference models, covering a useful range of shapes. From the gentle slope of a ramp to the steep pitch of a roof, any right triangle you might need for construction or land measurement would fall somewhere in this graduated catalog. You wouldn't calculate from scratch. You'd find the ratio closest to what you needed, and the tablet gave you the perfect whole number dimensions to build it. That turns the tablet from a list into a system. a scalable template. It shows they weren't just solving one problem at a time. They were building a unified solution for a whole class of problems. The order proves the intent. It reveals a mind thinking in terms of functions and relationships. They saw that the shape of a triangle, defined by a simple ratio, was the important variable, and they created a tool where you could dial that variable up or down and get a clean, exact answer every time. It's a concept so modern it feels out of place. A programmable reference table etched in mud. The ordered sequence is a map. A map of a mathematical landscape, but the territory it shows is much bigger than trigonometry. 322 is one artifact, but what it means shakes a grand story, the story of science itself. For a long time, the story went a certain way. That true scientific inquiry began with the Greeks. It came from philosophical wonder, from wanting to understand nature's order. Earlier knowledge from Egypt or Babylon was seen as practical, just useful rules, not a real, coherent science. This tablet forces a different reading. It's from a bureaucratic society, temple-centered, made for administrative needs probably, or architectural ones, yet it shows a level of consistency, a theoretical depth, a systematic generation. It meets a modern definition of scientific method. The scribe didn't just record a few useful triangles. They established a procedure, an algorithm, and used it to explore a complete set of possibilities within a defined parameter space. They saw a pattern in numbers. They made a rule to describe it. Then they tabulated the results in a logical format, a reproducible format. Observation, hypothesis, algorithmic generation, tabulation, these aren't just practical steps. They're the core activities of theoretical science. It suggests the engine for abstract thought wasn't just philosophy. It was also the demands of a complex civilization, the rigorous, repetitive demands, when you have to redraw thousands of field boundaries after every flood, and you need absolute fairness. You need more than a rule of thumb. You need a system that's provably correct, scalable, free from the bias of any single measurement. That need for perfect order in the physical world pushes the mind toward abstraction. It forces you to think about relationships, not just things, about the rule behind the result. So science, in this light, doesn't begin in a temple of philosophy alone. It also emerges from the accounting office, the surveyor's field, the scribal school. The origins of key methods, precise observation, data tabulation, algorithmic computation, are now anchored in clay, in the tablets of ancient Mesopotamia. This doesn't diminish the Greeks. They gave these tools a philosophical framework, a language of proof, but it recenters the timeline. It shows a much longer human project, more continuous. The pursuit of understanding through system and number isn't a sudden European awakening. It's a thread woven through urban civilization, wherever the challenges of scale and coordination demanded a truth beyond opinion. That Babylonian scribe, solving a problem of land or construction, was engaged in an act of pure science. They just wrote their discoveries on a tablet of mud. Instead of parchment, the spring flood had gone back. The Euphrates had cut a new curve along what used to be the straight edge of a barley field. The old stone markers were gone. You're the surveyor. Your job is to restore the original rectangle of the plot, the one in the temple records. The landowner's taxes depend on it. The community's sense of fairness depends on it. You have your tools, a long rope of woven reeds, a set of standard rods. First, you need to re-establish a perfect right angle for the corner. You could use the 3-4-5 method, but the ground here is soft near the new riverbank. A 3-4-5 triangle might give you a slope that's too steep or too shallow. For the long boundary you need to run, you need a different shape, a more acute angle. This is where something like the tablet becomes essential. You don't have the physical tablet with you, but you, or the scribe you trained under, would have known its key ratios. The tablet's first column lists a sequence of these ratios. They represent the steepness of the triangle's shortest side relative to its diagonal. You need a ratio that gives you a longer, more stretched out triangle, good for marking a long boundary line. Say you pick a ratio from the middle of the sequence. One that comes from a generating pair, like P equals 12 and Q equals 5. From the algorithm, that gives you a triangle with sides of 119, 120, and 169. Those are the template numbers. Now you scale them down to a size you can use in the field. You don't need a side of 120 units. You need a triangle you can lay out with your rope. So you divide each number by a common factor. Let's use 5. 120 divided by 5 is 24. 119 divided by 5 is roughly 23.8. 169 divided by 5 is 33.8. You can't measure fractions of a unit easily with a rope, so you might scale up a bit more for precision. But the point is, you now have a proportional template. For every 24 units on one side, the other short side is about 23.8, and the diagonal is about 33.8. That defines a specific non-standard angle. On the ground, you drive your first stake at the corner point that survived. Along the known good boundary, you measure out 24 units of your rope. You mark that spot with a second stake. That's one leg of your new right angle. From your first stake, you take a second rope. You need to measure out 23.8 units along the intended new boundary, but you can't easily measure 0.8. So you and your assistant use the known diagonal length as your guide. He holds the end of the diagonal rope at the second stake, measuring out 33.8 units. You hold the end of your 23.8 unit rope at the first stake. You both walk, tightening the ropes, until the marks where you're each holding meet. That meeting point is your third stake, the triangle formed by the 3 stakes. Sides of 24, roughly 23.8 and 33.8. That triangle contains a perfect right angle at your first stake. You've just constructed an accurate corner using a complex Pythagorean triple from a 4,000-year-old algorithm. The new boundary line is now established from that right angle. You can extend it, knowing the geometry is true. This isn't guesswork, it's applied computational mathematics. The tablet gave the pure number template. The surveyor translated it into physical space. This process turns abstract ratios into social order, into economic stability. It proves the tablet was more than a theory. It was the engine for rebuilding a civilization. One perfectly measured field at a time. That system of counting in 60s, it never really went away. It survived everything. The fall of Babylon, the rise of Persia, Alexander's conquests. It moved through Greek astronomy, into the Islamic world, and then into medieval Europe, and you still carry a piece of it. Every day, look at your clock. 60 seconds in a minute, 60 minutes in an hour. That division, it doesn't come from anywhere else. It's Babylonian math ticking on your wrist, or a compass, a protractor. A full circle is 360 degrees. Why 360? Because it's 6 times 60, a round number in their base 60 world. This isn't a coincidence, it's a direct inheritance, a thread of thought going back 4,000 years. The reason it survived is practical. It's brilliant in a sheer practical way. Our modern system is based in decimal. It works well for counting on fingers, but for dividing things up, especially without calculators, it can be clumsy. Think about dividing something into thirds using base 10. 1 divided by 3 is 0.3333 on forever. A messy, repeating decimal. Now base 60. 60 is a mathematical powerhouse. It can be divided cleanly by so many numbers. By 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, all without leaving fractions. In the ancient world, where calculations were done by hand, where precision in sharing resources was vital, this changed everything. Imagine you're a Babylonian administrator, dividing a grain harvest. Temple stores, worker rations, seed for next year. The totals are complex. With base 60, you have more ways to split those totals evenly. You can give 1/3 to the temple, no problem. That's 20 out of 60. 1/5 to the worker, that's 12 out of 60. The math stays clean, whole numbers. This divisibility made fractions far more manageable. It turned difficult operations into simpler ones. So when Greek astronomers and later ones needed a system to track the circular motions of the heavens, they took the Babylonian framework. It gave them the precision and flexibility they needed. The tablet 322 is a product of this system. Those huge, perfect Pythagorean triples, they're easier to generate and work with in a base 60 landscape. The Scribe wasn't fighting their number system. They were using its unique strengths to solve a complex problem. This longevity, it tells us something. It wasn't a cultural artifact that faded. It was a tool, so effective, so logically superior for certain tasks that it outlived its creators. It got embedded in the global language of science and time. Every time you check how many minutes are left or navigate using a bearing of 90 degrees, You're communicating in a small way with that anonymous Babylonian scholar. Their choice to build a mathematics on 60 proved so robust it became a permanent part of the toolkit. The clay tablet sits in a museum case, but its underlying logic is still alive. Measuring our days, charting our paths, that tablet wasn't some lone miracle. It wasn't a single stroke of genius that just happened to survive. The answer is in the clay itself and in the thousands of other tablets found with it. 322 is unique in its specific content, but it's far from alone. It's a star in a dense constellation. The broader collection of Babylonian mathematical tablets shows a tradition. We have thousands of them. Student exercises, multiplication tables, complex problem texts. A culture steeped in numerical reasoning. They were solving quadratic equations. They had procedures for compound interest. They worked with geometric problems, volumes and areas that would challenge a modern student. This wasn't a society with one brilliant scribe. This was a society that cultivated mathematical thinking as a core skill for its elite. Take another tablet known as YBC 7289. It's a small, round tablet, a practice exercise. A square is drawn on it. Across the diagonal, a number is written. That number in base 60 translates to 1.414212963. In our decimal system, that's an approximation of the square root of 2. Accurate to within 1 part in 60 million. That level of precision, for a number that's famously irrational, never-ending, is staggering. It tells us they weren't just calculating practical lengths. They were exploring numerical properties for their own sake. They had algorithms to compute square roots. They understood the relationship between the side of a square and its diagonal. This is the world 322 came from. A world where a scribe could look at a right triangle and see not just a shape for a field, but a set of pure numerical relationships governed by an elegant rule. The tablet's sophisticated use of generating pairs, its ordered sequence, its clean tabular format, all of that fits perfectly within the advanced, systematic mathematics we see on hundreds of other clay fragments. Its survival to reach us is a matter of luck. The right dig, the right collector, the right preservation. But its creation wasn't lucky. It was inevitable. It represents the pinnacle of a thriving, sophisticated intellectual culture, one that had been building this knowledge for centuries. Looking at 322 in isolation, it feels like a mystery. But when you see it surrounded by its peers, the mystery changes. It becomes a question of how much more they knew, and how much of that knowledge written on fragile mud tablets simply crumbled back into the dust, leaving only this one brilliant fragment to hint at the whole. The story of 322 after that first translation just sat there. For decades, it was in its museum case, a solved thing. Then, in the 21st century, the conversation started again. A new generation had tools the original scholars couldn't have imagined. They looked at the same clay and saw new questions. This is where digital archaeology meets the ancient thought. High-resolution 3D scans now capture the surface in microscopic detail. Every groove, every accidental scratch, the exact depth of each wedge. It's not just a better picture. It lets you study the scribe's technique, the order of the impressions, the angle of the stylus. You can look for erased numbers, corrected numbers, things invisible to the eye. You can model the object in a virtual space, measure it with a precision that doesn't risk the original. That technological leap turned a static artifact back into a dynamic text. A text you could examine from angles the scribe themselves might never have considered. And alongside the scans came data analysis. Mathematicians like Daniel Mansfield and his colleagues, they didn't just read the numbers. They fed them into algorithms, searching for patterns a human eye might miss. They tested thousands of hypothetical rules against the tablet's sequence, asking not just what the scribe did, but what they chose not to do. Why these 15 triples in this exact order and no others? The digital tools let them simulate the ancient mathematical landscape. To map all possible outcomes and see where 322 sits on that map. That approach, history, pure math, computer science, it created a new framework. It moved past asking, is this trigonometry, to asking, what kind of trigonometry is it? The modern reanalysis suggests it's more elegant, more complete than we first thought. A system built on exact ratios and perfect squares, avoiding the irrational numbers that complicate the Greek system. It was a trigonometry of harmony, not approximation. This ongoing scrutiny shows something. Ancient artifacts aren't dead things with one fixed meaning. They're living documents in a continuous conversation with the present. Each generation brings its own tools, its own question, its own perspective. The clay tablet doesn't change, but our understanding of it evolves. As our computational power grows, as our frameworks expand, these 4,000-year-old numbers find new voices. They speak about a universal drive. To find order, to build systems, to encode the world in symbols. The work on 322 now is a collaboration across time. A modern researcher staring at a high-resolution screen is engaging in the same act of inquiry as that Babylonian scribe staring at damp clay, both using the best tools of their age to uncover a pattern hidden in the numbers. The revelation is never truly finished. With every new technological lens, every fresh theoretical question, the tablet offers another piece of its secret. It reminds you that history isn't a locked vault. It's an open field. And the most important discoveries often come from looking at an old puzzle and daring to ask a completely new kind of question. Discovering something, what does that even mean? This tablet makes you ask that. We see 322 and we call it trigonometry. We give it our word from our Greek tradition. But the Babylonian scribe, they weren't thinking about trigonometry. They were solving a measurement problem, a problem of proportion, using their own mathematical language. They found these deep truths about right triangles, but they packaged that discovery in a framework that was completely different from what came later, and that points to something deeper. That mathematical truth might exist on its own, out there in some abstract space. The relationship between the sides of a right triangle, it's a constant. It was true before Babylon, before Greece, before anyone drew a shape in the sand. But how a culture finds that truth, the path it takes, the language it uses to express it, that's entirely human, entirely cultural. The Babylonians expressed it through ratios of whole numbers, through these elegant tables made by a clean algorithm. The Greeks later expressed it through geometric proofs, through the language of angles. They were both looking at the same mountain but climbing from different sides, describing the view with different words. Neither description is the mountain itself. Both are valid maps. 322 is a map drawn in the language of administrative precision, of base 60 harmony. It's a complete system, a functioning system. It challenges that comfortable story we tell, that history is a straight line of progress leading to us, to our modern understanding. That earlier ideas were just clumsy steps toward what we know now. This tablet shatters that linear view. It reveals a mosaic, a landscape where different civilizations built different but fully realized intellectual structures to solve the same eternal puzzles. The Babylonian approach wasn't a rough draft. It was a finished masterpiece in a different style. One that was, for its specific purposes, maybe more elegant, more exact than the system that eventually replaced it. So when we ask who discovered trigonometry, the answer gets wonderfully messy. The Babylonians discovered a form of it. The Greeks discovered another form. Both groups uncovered a piece of the same timeless reality, but they held it up to the light and saw different colors refracted. It shifts the history of ideas from a simple relay race, passing a baton forward, to a chorus of many voices, all singing different parts of the same grand, universal song. Our task isn't to crown one voice as the first or the truest, but to listen to the harmony they created together. Across the sunlight came through a high window, dust in the air, a low wooden table. The room was quiet, just the sound of a reed stylus, a soft scrape, a faint tap against the clay. This was the tablet house. And someone was working there. Their hands were steady. One hand held a damp slab of river clay, cool, pliable. The other hand guided the stylus, pressing marks into the surface, wedge-shaped marks, precise. Each press was a commitment. There was no backspace, no eraser. A mistake meant starting over, kneading the clay back into a blank lump. The numbers they were writing were enormous, tens of thousands. To calculate them, they used a mental algorithm, a set of rules held in memory. They chose starting pairs, did the multiplication, the subtractions, probably on a separate scratch tablet. And now they were transferring the final results, the perfect results. The concentration was total. This wasn't just copying, it was the final act, a long, intricate calculation. A single slip, a vertical wedge instead of a corner mark, and the row was flawed. The tool was compromised, so they focused. The world narrowed, down to the scored into the clay. The sequence of numbers that had to fill it. Who was this person? We'll never know their name. They were one of many scribes, a graduate of a rigorous system. Their training started young, mastering hundreds of cuneiform signs, memorizing lists, trees, stones, professions, learning the precise administrative language of the kingdom. Mathematics was a core pillar. They practiced multiplication, reciprocals, until it was instinct. They solved word problems about digging canals, dividing silver. They learned not just to calculate, but to think in a structured way, a procedural way. This tablet 322 was their masterpiece, the imprint of a mind trained to find order. Their motivation might have been practical, to create a definitive reference for surveyors, or it might have been something quieter. The satisfaction of seeing a beautiful pattern emerge from a rule, and the desire to preserve that pattern in a permanent form, a usable form, in its neat columns, its flawless ratios. You can sense a pride of craft. This wasn't a rushed administrative record. It was a tool of elegance and power, deliberately made. That person, their breath, the focus in their eyes, the slight pressure of their fingers, it all ended over 3,700 years ago. But in the silent, ordered language of these numbers they reach across, we aren't looking at a relic of a civilization. We're looking directly into the working mind of a single, skilled human being, a reminder. History in all its vast complexity is built by individuals, thinking, solving, and leaving a mark. That knowledge traveled along routes that were already old. Caravans on the royal road, ships across the Mediterranean. Armies moved, and with them came scribes, translators. Ideas were a kind of cargo, high-value cargo. Mesopotamia had been a crossroads for centuries, a hub for astronomy, for mathematics. Its influence spread out, to Egypt, to the Hittites, and then eventually to Greece. There's no direct text, no Greek record saying they learned this from Babylon, but the conditions were there. Alexander's conquests changed things. The 4th century before the Common Era, he was tutored by Aristotle, carried that curiosity with him. He founded cities like Alexandria, and he left Greek administrators behind in the heart of the old Babylonian Empire. So for the first time, you had institutions where Greek and Babylonian scholars could be side by side. The library at Alexandria aimed to collect everything. It's hard to imagine they ignored the Babylonian records. The astronomical records, the mathematical ones, a civilization they now ruled. This is when that hidden river of knowledge might have surfaced. Into the open, a scholar like Hipparchus, called the father of trigonometry. He worked in the 2nd century before the Common Era in Rhodes and Alexandria. His work needed long-term data, observations over centuries, and only one civilization had that, the Babylonians. Their records of lunar cycles, planetary movements. Hipparchus used that Babylonian data. We know he did. And from using their astronomical records to absorbing their mathematical techniques, that's a very short step. Calculating celestial positions ties directly to the geometry of triangles. So did the Greeks know? It wasn't about copying, it was an inheritance. The Greek tradition was different. They wanted universal proofs, elegant geometry. The why, the Babylonian approach was about the how. Practical, algorithmic. A Greek mathematician seeing Babylonian ratio tables wouldn't just transcribe them. They would dissect them. They'd ask what principle made it work. And in answering that, they transformed the tool into a theorem. They refined it through their own lens. This transmission wasn't a single event. It was a slow seepage over generations, through trade in Ionia, through scholars traveling to Egypt, through the Hellenistic world itself. The tablet suggests that river was there, flowing beneath what we call history. It changes the story from isolated genius to connected minds. The Greek achievement becomes a translation, a brilliant translation of an idea into a new language of thought, and that translation carried it forward for 2,000 years. That tablet changed everything, but what if it hadn't? If the looters in 1922 had dug a few feet to the left, or if Edgar J. Banks had just put it in a crate that got lost, or if the scholar who saw it first just saw a list of numbers, not the pattern. In that world, 322 never gets found. Our history books stay the same. The story is clean. The Greeks invented advanced math. Pythagoras discovered his theorem. Hipparchus founded trigonometry to map the stars. This brilliant abstract thought, this Greek miracle born from philosophy. The civilizations before, like Babylonia, their footnotes. Good at astronomy, good at law, practitioners, not theorists. Their math is just utilitarian arithmetic, a tool for bureaucracy, not a science of patterns. The timeline of human achievement looks shorter then, and it looks incredibly localized, confined to one peninsula. The sophistication of old Babylonian thought 1,000 years earlier stays in shadow. We underestimate an entire civilization's capacity for abstract reasoning. We miss that earlier chapter, where the demands of a complex society, surveying, building, administering, push the mind toward the same theoretical heights, just expressed in a different language. Our understanding of innovation gets skewed. We lean into the myth of the lone genius, the sudden flash in a vacuum. We don't see the long, collaborative groundwork that makes those flashes possible. This counterfactual shows a fragile truth. Our grasp of the past isn't solid. It's built on fragments that survive by chance. A fire, a flood, the decay of papyrus, the decision of a single collector. Any of that can erase a legacy. A world without that tablet is a world with a story about ourselves. It reminds you, history isn't just what happened, it's what we have found, and what we've been able to understand. Every artifact is a key. And some keys unlock not just a room, but a whole forgotten wing of the human mansion, filled with light and thought we never knew was there. The clay is in our hand, the numbers are there. After all the decoding, the pattern work, the history, one question stays. Why was this made? Why go to such lengths in that time and place to make this specific, ordered table? The answer isn't one sentence, it's a set of possibilities. Each one shows a different part of that ancient mind. Maybe it was a teaching tool, a final test for the best students in the scribal schools, not to test memory, but to challenge their grasp of a powerful algorithm. A master teacher could have given the problem, generate a complete, ordered set of Pythagorean triples using the rule of reciprocals. The student's job was to execute it flawlessly, to show not just calculation, but systematic thinking. The small copying errors we see might be the marks of that pressure. The human touch in a perfect mathematical exercise. So the tablet becomes a diploma, a certificate of mastery over a complex, abstract system. Or it was the opposite, a reference manual for a master surveyor or architect. Think of their projects. The ziggurats, those step pyramids reaching up, required perfect angles repeated thousands of times. The canals needed consistent slopes for water flow. For that kind of monumental, state-sponsored work, approximation wasn't acceptable. You would need a master table, kept in a temple or palace archive. A senior engineer could consult it to find the exact whole number template for any required slope. So every team across the kingdom built to the same precise standard. Here, the tablet is a blueprint, a tool for imperial coordination and control. Then there's the pure possibility that it was an intellectual demonstration, a proof of concept. The scribe had discovered or been taught this elegant generating algorithm. They saw its power to create an infinite series of perfect triangles, and they wanted to showcase that power, to map its output in a beautiful, logical sequence. The ordering by decreasing ratio wasn't just practical, it was aesthetically pleasing. It showed the algorithm's range and consistency. This wasn't for a field or a building, it was for the pattern itself. So the tablet is a manifesto, a declaration that numerical relationships could be explored, cataloged, and understood. But the most compelling answer isn't one of these alone. It's all of them woven together. It speaks of a culture that didn't separate these realms, where training the elite, building the monumental, and pursuing abstract knowledge were part of a single, unified endeavor. The creation of the tablet was an act of both profound practicality and profound intellectual ambition. It was a testament to a worldview that saw beauty and order in numbers, that invested immense resources, time, training, clay, careful thought, into forging precise, scalable tools to understand and shape their world. The ultimate why is this: they made it because they could, because their civilization had reached a point where such a synthesis of need, skill, and curiosity was not just possible but necessary. The tablet stands as a perfect artifact of that moment, where a human hand pressed a rule into clay, and in doing so touched a truth that would echo for. The clay tablet is in New York now. It's in the collection at Columbia's Rare Book Library. They keep it in a room with special air, special light. It's not for surveying anymore, it's become a key to history, but it's so fragile. After 4,000 years, the air itself can damage it, even a touch. So studying it, just turning it over in your hands, that's a risk. That's the problem with these things. You have to protect them to understand them, but you have to understand them to know what you're protecting. So preservation is this careful balance, a silent job. Making sure this piece of fired mud lasts another 100 years for the next questions. Now there's a way through that problem: digital imaging. high-resolution scans. They create a perfect three-dimensional copy. Every wedge mark, every crack, every curve of the surface, it's all there. This digital version, it's a new artifact, one you can send anywhere. A scholar in Berlin or Sydney can look at it up close the same as if they were in the vault. That changes things. It breaks down the old walls, the physical walls, the geographical ones. This tablet came from an ancient bureaucracy, and now it lives on the internet. That's a kind of continuity. The medium changes, but the impulse doesn't. The drive to share information, to analyze it, that stays. And this access lets the discoveries keep coming. A century ago, Edgar Banks had this tablet. He saw a curio. Then Otto saw a math table. Then Daniel Mansfield and his team saw a different trigonometry. Each generation brings new tools, new questions, to the same object. So by preserving the original and by putting a digital copy out into the world, you're inviting the next generation in. A future mathematician with some AI we can't even picture yet might see a pattern we've overlooked. A historian might link its format to other texts we haven't cracked. The story of this tablet isn't over. We won't write the last chapter. Our job is just to pass the key along, keep it intact, so others can open new doors. In that big mansion of human thought, the real legacy of this tablet isn't just what it's already taught us. It's that it's still here, ready to teach again. The story of this tablet isn't finished. We solved one mystery and then we found others. The big questions now aren't really about the numbers. They're about the life around them. We know it was a sophisticated tool, but what was the exact moment of its use? You have to picture the context. Was it a reference scroll in a master's library, pulled down to settle a complex calculation, maybe for a temple's foundation? Or was it itself a lesson? A final project for a student to show they'd learned the whole generating algorithm. The small errors suggest human fallibility, but were they the marks of a learner under pressure, or a master scribe working late by lamplight? We may never know the specific classroom, or the specific building site where this clay was consulted, and that leads to a possibility. 322 is not alone. It can't be. A work like this implies a tradition. It implies teachers and students and other practitioners using these methods. So where are their tablets? The broken left edge of ours hints at a larger, more complete original. Could other copies be out there? More advanced treatises, maybe? Sitting in museum basements, miscatalogued among administrative records, or still buried. Waiting in the Iraqi soil, intels not yet excavated, or sites already lost. Every undiscovered tablet is a potential revolution. A chance to see the full scope of this Babylonian vision. Our technology now offers new ways to ask. Advanced imaging, like reflectance transformation imaging, can highlight surface variations you can't see. Could a scan of the broken section reveal a ghost of a mark, a trace of the original column that listed the key generating numbers? Could spectral analysis detect the chemistry of a lost pigment, a line drawn to guide the scribe's hand that's since faded away? We're not limited to what the eye can see anymore. We can use light as a delicate probe. Seeking answers in the microscopic landscape of the clay. This is the nature of historical discovery. The story of 322 isn't a closed book. It's a conversation across 4,000 years. Each answer we get becomes a platform for new questions, more fascinating questions. It reminds us that our understanding of the past is always provisional, always subject to revision, with the next fragment found, the next scan completed. The next mind looking at the old numbers with fresh eyes. The tablet's final lesson might be this: true knowledge doesn't end with a solution. It begins with a deeper curiosity. The map of mathematical history is wrong. We've been using an old chart. It started in Greece. But now we have a new landmark. 1,000 years earlier, hundreds of miles to the east. 322 is the evidence. It proves beyond doubt that trigonometry and complex number theory were Greek inventions. They were a fully realized system in ancient Mesopotamia, over 1,000 years before Pythagoras was born. This isn't a footnote, it's not a lucky guess. It's a complete algorithmic tabulated system. It shows a mastery of abstract relationships we never gave them credit for. We think of Babylonia as the dawn, the first clumsy steps. This tablet shows them running a marathon while others were learning to walk. The implications are profound. It forces us to expand our view of human ingenuity. The story isn't a linear relay race anymore. The baton doesn't pass neatly from one culture to the next. It's a mosaic, a chorus. Different civilizations with their own needs and perspectives arrived at profound insights independently. The cradle of mathematics wasn't one place, it was many. Greece gave it philosophy and proof, but Mesopotamia gave it system and scale. They built the first robust framework for calculation. The base 60 system that still structures our time and our circles. They developed the administrative mindset, turning complex problems into repeatable procedures. 322 is the crowning jewel of that tradition. It shows the drive to find order in the universe, to encode it in numbers. That's a fundamental human impulse. It didn't come from one moment of isolated genius. It came from the sustained, collaborative effort of a complex urban society. Rewriting this doesn't diminish the Greeks. It enriches our entire history. It adds a rich, earlier chapter, full of its own characters, its own language of discovery. It reminds us that brilliance isn't confined to one time or one people. It's a capacity we've always had, waiting for the right conditions to express itself. In clay, in stone, in the silent, enduring language of numbers, the real power of this tablet isn't just the numbers, it's the quiet challenge it makes. For more than 100 years, it was in a collection. Its deeper meaning was hidden by what we assumed about where genius comes from. 322 is a monument to a lost world of thinkers, people who saw the universe not in angles but in ratios, elegant ratio. They expressed profound truths. They did it with the simple press of a wedge into clay. Their revolution was quiet. It was written in the language of administration, but its echo now reshapes our whole timeline. Our timeline of human thought. This artifact reminds us, history isn't a single bright thread. It's a vast tapestry woven with threads we haven't found yet, full of quiet revolutions waiting in archives, in museum basements, in the ground beneath our feet. All they need is the right key, the right question to bring their story back into the light. The journey of mathematics is longer, it's richer, more beautifully interconnected than any textbook shows. It's a story still being written. With every new fragment we find, with every old puzzle we see through fresh eyes.